Today we are going to discuss elimination reactions. When a haloalkane with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, there is elimination of hydrogen atom from beta carbon and halogen from the alpha carbon atom. Location of alpha and beta carbon in the molecule. Carbon on which halogen atom is directly attached is called alpha carbon, and the carbon atom adjacent to that is called the beta carbon. Now let's try to understand it. Here X is the halogen atom, or it can be the functional group. So the carbon to which functional group is bonded is called alpha carbon, and the carbon next to it is called beta carbon, and the carbon next to beta is the gamma carbon. Here it is written when haloalkane with beta hydrogen is heated with alcoholic KOH. Alcoholic KOH. So let's take the example of chloroethane. Now draw the structure of chloroethane. There are two carbons. To first carbon chlorine is bonded, and at the rest of the position hydrogen is there. So write down the hydrogen in rest of the position. When alcoholic KOH react with chloroethane, this alcoholic KOH will act as a base and it will abstract hydrogen in the form of H plus ion. When it abstracts hydrogen in the form of H plus ion, this bond, sigma bond, will move between the carbons, and chlorine will be removed in the form of Cl negative ion. So here you will get the structure ethene. Here hydrogen is bonded to the carbon, and as the sigma bond moved between the carbons, you will get the double bond. Here hydrogen, here is another hydrogen. Chlorine left the molecule in the form of Cl negative ion. Now let's re-examine the example given in the book. Here this is the base which abstract H plus from the molecule, and the sigma bond moved between the carbon, and halogen leave the molecule along with its bonding pair of electrons. So as a result of it, you will get alkene. Base will make bond with the hydrogen. So here B is bonded to hydrogen, and X negative ion, which is a leaving group, left the molecule. Now let's read from the book. As a result, an alkene is formed as a product. Since beta hydrogen atom is involved in elimination, this is often called as beta elimination. If there is a possibility of formation of more than one alkene due to the availability of more than one beta hydrogen atom, usually one alkene is formed as a major product. These forms part of a pattern first observed by Russian chemist Alexander Saytzeff, also pronounced as Saytzeff, who in 1875 formulated a rule which can be summarized as: in dehydration reactions, the preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atom. Thus, 2-bromopentane gives pent-2-ene as the major product. Here 2-bromopentane is given, and this is the alpha carbon to which bromine is bonded, and the carbon next to it is the beta carbon. So here this is the beta carbon, and this also a beta carbon. When this beta hydrogen is removed, you will get pent-1e. Double bond will be formed between first and second carbon. And if the other beta carbon is removed from the molecule, double bond will be formed between second and third carbon. And as a result of it, pent-2-ene will be formed. Pent-2-ene will be formed as a major product. It is formed up to 81%. And this is the rule explained. The preferred product is the alkene which has greater number of alkyl groups attached to the doubly bonded carbon atom. In pent-2-ene, methyl is one alkyl group and ethyl is another alkyl group bonded to doubly bonded carbon. While in case of pent-1ene, there is no alkyl group bonded to doubly bonded carbon. Here there are two hydrogens are bonded, but there is no alkyl group. And on the other side, propyl group is bonded to doubly bonded carbon. So in case of pen-2-ene, there are two alkyl groups bonded to doubly bonded carbon, while in case of pent-1-ene, there is just one alkyl group bonded to doubly bonded carbon. That's why pen-2-ene is formed as a major product. Elimination versus substitution. Any chemical reaction is a result of competition. It is a race that is won by the fastest runner. A collection of molecules tend to do, by and large, what is easiest for them. An alkyl halide with beta hydrogen atom, when reacted with a base or a nucleophile, has two competing routes, substitution and elimination. Which route will be taken up depends on the nature of alkyl halide, strength and size of base or nucleophile, and the reaction conditions. Thus, a bulkier nucleophile will prefer to act as a base and abstract proton rather than approach the tetravalent carbon atom, and vice versa. Primary alkyl halide will prefer SN2 reaction. Secondary alkyl halide SN2 or elimination depending on the strength of base and nucleophile. And tertiary alkyl halide prefer SN1 or elimination depending on the stability of carbocation or the more substituted alkenes. Now let's try to understand it. Here it is given, this is the bromine and the carbon to which it is bonded is the alpha carbon. And this alpha carbon is bonded to another carbon. That means this alkyl halide is secondary alkyl halide. This is also secondary alkyl halide. Whether it undergo elimination or substitution, it depends on the type of nucleophile and the condition. Here the nucleophile is bulky. This is bulky nucleophile. Bulky nucleophile will prefer to act as a base. Here it will prefer to abstract the hydrogen from the molecule in the form of H+ ion, and the bonding pair will shift between the carbon and it expel bromine in the form of Br negative. While here this is the small nucleophile, it will act as a nucleophile itself. So it will directly attack on the alpha carbon and expel Br in the form of Br negative ion. That's why it undergo SN2 reaction mechanism. While with a bulky nucleophile, secondary alkyl halide undergo elimination reaction. In the beginning of this chapter, we have learned when alkyl halide react with aqueous KOH, it gives you alcohol. And today we have learned that when alkyl halide react with alcoholic KOH, it results in the formation of alkene. So how the action of alcoholic KOH and aqueous KOH are different from each other? Now let's try to understand it. In case of aqueous KOH, to make aqueous KOH solution, KOH is mixed with the water. And you know, when base is mixed with the water, it results in the formation of OH negative ion. So here it will produce OH negative ion when it is mixed with the water molecule. So this OH negative ion is a small nucleophile. So this OH negative ion will act as a nucleophile because it is smaller in size, and this is a strong nucleophile. That's why with the aqueous KOH solution, alkyl halide undergo SN2 or SN1 reaction mechanism depending on the type of alkyl halide. So it will undergo SN1 or SN2 reaction mechanism. Now come to the alcoholic KOH solution. To make alcoholic KOH solution, KOH is mixed with alcohol, so it can be ethanol, C2H5OH. When it is mixed with the ethanol, it will act as a strong base, and alcohol will act as a weak acid. So this strong base will abstract H+ from the weak acid alcohol, and it results in the formation of H2O plus C2H5O negative ion and K+ ion. So this C2H5O negative ion, now it will act as a nucleophile, and this is a bulky nucleophile. This bulky nucleophile will act as a base. That's why it will abstract H plus from the molecule. As we just have learned earlier, when alcoholic KOH is there, this is alcoholic KOH, and when it reacts with chloroethane. So here again I am writing the same formula. This is the chloroethane. So when alcoholic KOH react with chloroethane, in alcoholic KOH C2H5O negative ion is or which is a bulky nucleophile, so it will act as a base. So it will abstract H plus from the molecule. This bonding pair will shift between the carbon and it will expel chlorine in the form of Cl negative ion. And as a result of it, we will get alkene. CH2 double bond CH2 and Cl is removed in the form of Cl negative ion. C2H5O negative ion abstract H plus from the molecule. It will result in the formation of C2H5OH. So ethanol is produced. In the next video, we will discuss reaction with metals.